All right. Good morning, everyone. As I promised you, I graded your exam, graded them yesterday, and I posted them. I will give you, upload a complete solution over this weekend, okay? So you will know what you did wrong, what you did not do wrong. I did put, there are a grade letter beside your grade, okay? Were you able to see the grade letters or not? Hello? Okay. So there is a grade letter beside your name. This is where you stand. I did override some of them. I overrode some of them. So do not panic. Everybody's doing okay. Just keep working. That's all I ask. I noticed some of you used AI to generate some of the solution. They were wrong. AI is not always correct, or did not give you the correct formula. So please be careful. That's all I'm gonna say. Anything else? Okay, let's continue with what we were doing last time. If I can find my pen. There it is. Okay, so this is a problem on the exam. This was a problem on the exam. I think problem 6, maybe. So last time we need to solve u1 of n is lambda 1, mu1, 3 mu1, mu1 of 0 equal 1. The solution turned out to be 3 to the n. We got a mu2 to power mu2 of n 3 to power n minus 1. Okay, now we need to solve this one. This is a mu3 of n plus 1 equal minus 3 mu3 of n plus n3 n minus 1. Now, a lot of you use the formula wrong. This is supposed to be g of r, not g of n. So if you do this with a equal minus 3 and g equal n times 3 to power n minus 1, since mu3 of 0 is 0, this term cancels out, and you have this term here. Sum from r equals 0 to n minus 1 minus 3 to power n minus r minus 1, gr times r 3 r minus 1, that is 0. And that is minus 3 to power n minus 1, r equals 0 to n minus 1 minus 3 minus r times 3 r minus 1. That is minus 3 n minus 1, r equals 0, minus 1 to the minus r. This one I'm rewriting times 3 to power minus r, okay? Times r, 3 to power r times 3 to power minus 1. This comes out, and this one and this one, this and this cancel out, and then you are left with r times minus 1 minus r, but this is the same as 3 minus 1 is 1/3 minus 3 n minus 1, r equals 0 to n minus 1. This is the same as minus 1 to power r. Okay? Any questions? All right. So if I do some calculation, we're gonna do summation by parts. So we're gonna use this formula, k equal n0 to n minus 1, xk del xk del yk is equal to xk yk from k equal n0 to n minus k equal n0 to n minus 1 del xk e yk. All right. So I have this one here. So what do you think I should take? It seems like I'm gonna let x of r equal to, here r is k, x of r equal to r, and del y r equal -1 to the r. Okay? So that means del xr is r plus 1 minus r is 1, and yr is -1 to power r over -1 minus 1. Okay? So that is -1/2 minus 1 to power r. So what I did use is a to power r is a to power r over a minus 1. Okay? So, hence, mu3 of n is equal to 1/3 minus 3 to power n minus 1 times xkyk, xryr will be -1/2 minus 1 to power r times r from r equals 0 to n, okay, minus r equals 0 to n minus 1, del xk is 1 times eyk times -1 r plus 1. You see that? It's EYR. That is why E is -1 to power r plus 1. Okay, so let me erase this. And that is 1/3 -1 to the n minus 1. If I put r equal n, will be -1/2 minus 1 to power n times n minus 0. And this one is a plus -1 to power r over -2, r equals 0 to n. Okay? And so this is 1/3 -1 to the n minus 1, minus n over 2 times -1 to power n, minus 1/2 minus 1 to power n, plus r equals 0 plus 1/2. All right? And that turned out to be, I simplified it. What do I have? Okay, yr is, what did we do with y? -1/2. Okay, so this becomes okay. Minus r over 2 eyk is minus, so this becomes, oh, there's here 1/2. Okay, so this becomes plus 1/4. All right, and this is gonna give me, if you do the math correctly, this is going to be n 3 to power n over 18 minus 3 to power n over 36 plus minus 3 to power n over 36. Some of you got it correctly on the test. So that is mu3 of n. All right, so we're gonna now what we're gonna do is we're gonna go back, and we know the D's and we know the A. So what is my eraser? I lose it. Gee. I don't know what I did with it. So now this is the D0, that is D1, D2. And so according to the theorem, then AN is J equals 0 to n minus 1. Okay. Or J equals 0 to, okay. Let's see what the theorem says. Okay. The theorem says AN equals J0 to K minus 1, sorry. Mu J plus 1 of n dj. Now K is 3. This is the size of the matrix. So that is J equals 0 to 2 mu J plus 1 of n dj. So that is mu1 d0 plus mu2 d1 plus mu3 d3. Now you know everything. You know this, you know that, and you can multiply it together. And for the heck of it, I'm gonna give you okay. Okay, so this is going to be, I'm gonna give you the matrix just to show you something. It's 5 plus 2n over 6, 3 to power n, plus 1 minus 6n over 6 minus 3 to power n, and then 1 minus 2n over 3, 3 to power n, plus 6n minus 1 over 3 minus 3 to power n, and all over. So AN is this one here. You see how big it is? That is AN. And if you notice that A to power 0 is I. And that turned out to be 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, look at it. For n equals 0, this will be 5. Okay. Let's see, what is this? 1 minus 6 over 6. Okay. So you'll have 5/6 plus 1/6. That will be 1. And this one will be 0. This will be 1/3 plus 0 minus 1/3. This will be 1/3 minus 1/3, 0, and the other term will be 0. So that is A0. Okay? And also turn out to be that AN is symmetric. Okay? AN is symmetric. And now, if we are given x0, then xn equal a to power n, x0 is the solution. Okay? All right. Now we're gonna take a special case of special case. So now, suppose A is a 2x2 matrix, constant. Then put the algorithm simplifies to the following. 1, if the two eigenvalues λ1 and λ2 are distinct, then AN is λ1 to the n I plus λ1 to the n minus λ2 to the n over λ1 minus λ2 times A minus λ1 I. And this is n bigger or equal to 1. So that is, if A is 2x2 matrix and both eigenvalues λ1 and λ2 are distinct. Now 2, if λ1 equal λ2, then AN equal λn I plus n λn minus 1 A minus λ1 I. Okay? And bigger or equal to 1. All right? So you can easily now construct. But if it's 3x3 matrix, then this becomes really complicated. And you are very welcome to find a formula for that. I was able to find a formula for 2x2. Go ahead, be my guest, and try to find a formula for 3x3 matrix if all the eigenvalues are distinct. Then it will be difficult to do it for 3x3. All right, any questions? All right. Now we're gonna talk about non-constant system. Okay. All right. This is section 4.4. Time varying system. Time varying system. Okay. So basically, we're gonna consider x n plus 1 equal a to power a of n x n, and we're gonna call this is 4.4.1. So that is a system. So here A is K by K matrix. May not be constant, may not all its entry being constant. You know, if the entries are constant, we already discussed that, and all the result of this section belong to that. Okay. So definition, fundamental set of solution. All right. A set of K solutions of the linear system 4.4.1 are all defined on the set and not is called a fundamental set of solution on N naught, fundamental set of solution on N naught if the solutions are linearly independent. So they have to be linearly independent. So corollary, let AN be a K by K matrix with fundamental set of solution phi 1 of n, phi 2 of n, phi k of n, then the general solution, okay, of 4.41 is xn equals C1 phi n, sorry, phi 1 of n plus C2 phi 2 of n plus CK phi k of n. So that is a general set of solution. All right. Remember, each of these solutions is a vector. Each one of them is a vector. Remember how we did that before the constant matrix? So this is the same theory provided we talked about before, but we didn't call it that way because A was a constant matrix, easier to deal with. All right. So remember 4.41. Okay, definition. It says this is a fundamental matrix. Okay, a matrix solution phi n is called a fundamental matrix solution solution, or in short, fundamental matrix of 4.4.1 on an interval and not if its columns form a fundamental set of solution. Okay. In addition, if phi of n naught equal I, then phi is called the principal fundamental matrix solution, or in short, principal matrix. Okay. So basically, what do? It's like what we did for the constant matrix. We found the solution phi1, phi2 based on the eigenvalues, eigenvectors. And you list the metric phi. Before we called it phi of n. Now we cannot call it with a capital phi. And so its columns are the solution formed from the eigenvalues and eigenvectors. Here is the same, but you don't know how to find the solution if the matrix A and A is not constant. It becomes very difficult. Okay? So this is nothing new, basically. And we have a theorem 4.41 says the matrix phi n. So let me, okay. So, okay, I will say something about it. The matrix phi n is a fundamental matrix of 4.41, okay, of n naught if and only if A, P, n is a solution of xn plus 1 equal a n xn, okay, and B, determinant of phi at n naught is different from 0. And n naught is any number. Okay? All right. So if an is A, then phi n is A to power n, the principal matrix. Okay? It's called the principal fundamental matrix. All right? All right. Okay. Here's an example. Let's take a look at xn plus 1 equal a xn, and I am looking a constant, 10, 4 minus 24, 10. Then phi n is 2 to the n, 3 minus 2 minus 1 to the n, 1 minus 1 to the n, minus 6 plus 6 minus 1 to the n, minus 2 plus 3 minus 1 to the n. Okay? And you can check that phi n plus 1 equal a phi n, and determinant of phi n is not 0. Okay? For all n. So you can easily check that. And clearly, phi 0 is I, and so in this case, phi n is a to power n. Because phi 0 is a to power 0. So if you do it at n to power 0, you will get 1, R, identity matrix. Well, that's easy. This will be 1, will be 3 minus 2 is 1, will be minus 6 plus 6, 0, 1 minus 1, 0, minus 2, plus minus 2, plus a 3, that will be 1. So you can see at 0, it is the identity matrix. And then you can see the determinant phi n is 3 minus 2 minus 1 to the n times minus 2 plus 3 minus 1 to the n minus 6 plus 6 to power minus 1 to the n times 1 minus 1 to power n. Okay? So if you simplify this, this will be minus 6 plus 9 minus 1 to the n plus 4 minus 1 to the n minus 6. And then you have minus 6 plus 6 minus 1 to power n plus 6 minus 1 to power n and minus 6. Okay? All right? And if you simplify this, this and that go away with this and this. And then we have what the hell? Oh, we have 2 to the n times 2 to the n. Why am I getting 0 here? I should not, should I? Minus minus 6 plus 6 times 1 minus 1 minus. So minus 12 plus 12, 6, 9 plus 4. I should not be getting 0. I should be different than 0. All right, let me check what's going on here. 3 minus 2. All right. For n at n0, so you have. All right. Do you see any wrongdoing here in my calculation? Determinant based on the other one, determinant of phi n naught Okay, let me check this later. I'll get back with you next time. Okay. So we verified phi 0 equal I. This should not be 0. Let me go over it one more time. Will be 3 minus 2 minus 1 to the n times minus 2 plus 3 minus 1 to the n. This would be minus 6 plus 9 plus 4 minus 6. Okay, minus 1 minus 1 to the n times minus 6 plus 6. So we have minus 6 plus 6 to power minus n plus 6 and minus 6. So I have 6 minus 6 minus 6 minus 12 plus 12 go to 0. 9 plus 4. Oh, gosh, I cannot add. Guys, are you paying attention to me? That is 13 minus 1 to the n minus the 12 minus 1 to the n, and that is minus 1 to the n, and that is never 0. For some reason, I was saying 9 plus 4 is 12. Okay? Is anybody paying attention here? All right. But I mean, you can speak up. You know that? So the determinant is never 0. Okay? All right, for all n. So that is verify this. All right. Now, then we know that if phi of n is a fundamental matrix, if is a fundamental matrix, then C of n equal phi of n times C, where C is a non-singular k by k constant matrix, is also a fundamental matrix solution. Of 4.4.1. Is that what we called it? Yeah. So that is phi of n plus 1 equal a psi n. Okay? Now, if we consider, okay, consider 4.41 with x of n naught equal x naught. That is we're looking at xn plus 1 equal an xn, and xn naught equal x naught for n bigger or equal to n naught. Okay? And if phi n, a fundamental matrix, of 4.41, then xn is equal to phi nc, okay, where c is phi inverse of n naught times x naught, is the solution of 4.41 with x of n naught equal x naught. Okay? All right. Let's take a 5 minutes break and come back. Okay? I'll see what time it is. You cannot focus without Lily. Hey, you didn't reply if you would like to have her on August 2nd for the whole day. You can have Lily on August 2nd if you want.
I'll be doing a Tough Mudder in Indiana. I won't be here, unfortunately.
Yeah. I don't want to take her to a daycare, you know. She doesn't do very well. She cries all night. Dog kennels are bad. All right. So now I'm hoping I finish early today, and then we start stability next time. Okay. All right. Okay. So now we're gonna, this is section 4.5. Non-homogeneous systems. So we're gonna consider the non-homogeneous system xn plus 1 equal an xn plus gn. And here, just a second. Sorry about that. So here A is a K by K matrix, and Gn is a K by 1 vector. So they're both defined on a set and not. And recall what this set is. This is n naught plus 1, and so forth. This is what this set. I'm just reminding you. Okay. So, and then we're going to consider it is corresponding. Okay, so we're going to call this is 4.5.1. Its corresponding homogeneous system is xn plus 1 equal an xn. And we're gonna take a look here that xn naught equal x naught, 4.5.1. And this is 4.5.2. Okay. Is the writing dark enough for you guys? Okay. From section 4.4, we know the solution of 4.52 can be written as, and what I'm gonna call it xh of n is phi n of c, where phi n is the fundamental matrix of 4.52, and c is a k by 1 vector. Okay. So this is what we know so far. From that section, we know how to talk about this, not this one. Okay? So we're gonna talk about it. Now, oops, did I run? Okay, so I'll be like that. All right. So if xp of n is a particular solution of 4.51, then the general solution of 4.51 is xn equal to, okay, is xn equal to xh of n plus xp of n. There you go. Okay? All right. So the question is, what does the solution look like? All right. So here is a big theorem for you guys. All right. Okay, so we're gonna have a big theorem. All right. So theorem 4.5.1. Okay. It says the general solution okay xn of 4.51 let me put it this way. Xn is a solution of 4.51 if and only if xn is given by phi n, phi inverse of n naught, x naught plus s equal n naught to n minus 1 phi n plus 1, sorry, phi of n, not n plus 1. Phi inverse of s plus 1 times g of s, and this is 4 pound 5.4. Okay,
Hey, can you rotate that whiteboard? Just a little glare on the right side. Yeah, that's money. Yes, perfect.
all right. Okay, so where phi n is the fundamental matrix solution of 4.5.2. Okay, so the proof. Suppose xn is given by 4.5.4. Then x of n naught equal phi of n naught, phi inverse of n naught, x naught, plus s equal n naught to n naught minus 1, phi of n naught, phi inverse of s plus 1 g of s. This is 0. Can anybody tell me why it is 0? So, can anybody tell me why this is 0? Hello? You remember we agreed on the summation s equal b a to b of x of s, that is 0 if b is less than a, isn't it? We agreed on that. N naught minus 1 is smaller than n naught. So this summation is 0. Don't forget that. Okay? So basically, what I showed is, I showed this one is correct. Now I need to show that xn satisfies 4.51. Let me show that xn given by 4.5.4 is indeed a solution or is does indeed satisfy xn plus 1 equal an xn plus a gn. Okay? All right. So if xn is given by 4.54, then xn plus 1 is phi n plus 1 phi inverse of n naught x naught plus s equal n naught to n phi of n plus 1 phi inverse of s plus 1 g of s. Did you see that? Okay. Since phi n plus 1 equal a n phi n, we have xn plus 1 equal to a n phi n phi inverse of n naught x naught. Okay. Here, phi n plus 1 is, I'm going to take this out, plus a n phi n summation s equal n 0 to n phi inverse of s plus 1 g of s. I replace phi n plus 1 with a n phi n. Okay. So far, so good. All right, so we need to evaluate this one at n. If I evaluate s at n, so this is a n phi n phi inverse of n naught x naught plus a n phi n. This is at n phi inverse of n plus 1 gn plus s equal n 0 to n minus 1 phi inverse of s plus 1 g of s. Okay. So, do you see where we are headed? Okay. So, what are we gonna have? So this is a n phi n phi inverse of n naught x naught. Let's multiply this plus a n phi n. What about this one? This. What is phi inverse of n plus 1? Phi inverse of n plus 1 is phi inverse of n a inverse of n gn plus an pn S equal N0 to N minus 1 phi inverse of S plus 1 GS. Okay, so we're almost done. So this is AN phi N phi inverse of N naught X naught plus, let me do this one, AN S equal N naught to N minus 1 phi of N phi of S plus 1 GS. This one here, this term is this term here. You see that? I can take the phi n in because the summation is done over S. Now, what is this term now? This one is I, so this term is a plus a G of n. The whole term here, the whole term is this one. So this is equal to AN phi n phi inverse of N naught X naught plus S equal N naught to N minus 1 phi n phi inverse of S plus 1 G of S plus G of n. Do you see it? I factor AN, so I got this term plus this term here. I factor AN, I got this term, X naught plus this term here, and I close the factor plus GN. By the way, guys, take a look here. What is that term here? Phi n, phi inverse N naught X naught. S equal N0 to N minus 1. Phi n, phi inverse S plus 1 GS. Hallelujah. So this is AN XN plus G of n. There we go. You see how we verified it? Take a look at it. Okay? Just take a look at it, see what we did. All right. Now, so this way we did. This is if and only if a proof. Okay? Look at it. This is if and only if. So now we need to look at the other way around. Next, we show if Xn satisfies 4.51, then it is given by 4.5.4. There. Okay, so this is what we need to show. All right, so we know XH of n is phi of n times c. That is the solution. This is the solution of 4.5.2. Let xp equal to of n equal to phi n un, where un is to be determined. Be the particular solution of 4.5.1. So here, phi n is the fundamental matrix solution of 4.5.2. So we need to find un. All right. So what do we know? So we need xpn plus 1 equal an xp of n plus g of n. We already know that. Okay? So substitute xp of n plus 1 equal to an phi n un plus gn. Okay? Are you with me? All right. So multiply both sides with phi inverse of n plus 1. So we're gonna get un plus 1 equal phi inverse of n plus 1 an phi n phi n un plus phi inverse of n plus 1 gn. Okay? Now, an phi n, this is phi n plus 1. So this is phi n plus 1 phi n. So this is un phi n. Okay? No, this is un only. So this is un plus phi inverse of n plus 1 gn. This is what you have. Okay? So, or del un, take un over there. You get un plus 1 minus un. That's del un equal phi inverse of n plus 1 gn. Okay? Sum both sides from S equal n naught to n minus one. Okay? So we're gonna have un S equal n naught to n minus one phi inverse S plus one GS. That's good work. Then xp of n equal phi n un, and that is S equal n naught to n minus one phi n phi inverse of S plus one GS. Wow, I got xp. Finally, the solution of 4.51 is xn equal xh of n plus xp of n. That is xn equal to, remember what xh of n. Xh of n we already know. This is fn. This is phi nc plus s equal n naught to n minus one phi n phi inverse of s gs. Now, let's define c. So we know xn naught. We know x naught equal to xn naught equal to phi n naught c plus 0. Again, if I replace n by n naught, the sum from n naught to n naught minus 1 is automatically 0. And this implies x naught, this multiplied by the left. So this implies phi inverse of n naught, x naught equals c. So now, put in here. Finally, xn equal to phi n, replace c by that, phi inverse of n naught x naught plus s equal n naught to n minus 1 phi n. Sorry, this is s plus 1. It's okay. Phi inverse of s plus 1 g of s. And guess what? That is, which is 4.5.4. Take a look at it. Phi n, phi inverse of n, 4.54, phi n, phi inverse of n naught x naught, s equal n0 to n, phi inverse s plus 1 g of s. Oh, that is a very interesting proof. Okay? What do you think? Now, corollary, if an equal a, then a to power n is phi n phi inverse of n naught. Okay? All right? And if sorry, let me put it this way. Let's do it. If then an equal a, then a to power n. Or, okay, then how do I want to say it? An minus an equal to phi n. Okay, let's put it this way. And then if you look at this formula, n naught x naught plus s equal n naught to n minus 1 phi of n, phi inverse of s plus 1 g of s. So this one is an. Now this one, phi inverse of a naught. So phi inverse of a naught equal a n naught inverse, that is a minus n naught. So that will be minus a minus n naught x naught plus s equal n naught to n minus 1. Phi n will be an times phi inverse of s plus 1. All right, so phi of s plus 1 is a s plus 1. So phi inverse of s plus 1 equal to a minus s minus 1. And so that is a minus s minus 1 gs. So that is a n minus n naught x naught plus n equal n naught to n minus 1 a of n minus s minus 1 g of s. Okay, and that what the formula be. Any questions? For example, let's say an is minus 1 to the n, 0, 2, 1 minus 1 to the n, 0, minus 1 to the n, and 1 minus minus 1 to the n, and 0, 0, 1. So let's say this is an. And you want to form an minus a naught, then an minus a naught is minus 1 to the n minus a naught, 0, 2 of 1 minus 1 to the n minus n naught, and 0 minus 1 to the n minus n naught, and 1 minus 1 n minus n naught, and 0, 0, 1. You see it? Okay. And notice where n equal n naught, a0 is 0 is 1, 0, 0, 0, 1, 0, 0, 0, 1. That is I. Okay. Take a look at it. When n equal n naught, minus 1 to power 0 is 1. That is 0. And here you will have minus 1 to power 0 is 1. 1 minus 1 is 0. Okay? And here you will have 0, 0, 1. This will be, let's see, 1. Oh, yeah, this will be 0, and then 0, 0, 1. You will see what you get. So this one mean n0 is 0, correct? This one is this mean. But if you take n0 to be non-zero, then you need to raise every exponent in n to n minus n naught. Now, I'm going to stop here. I'm going to ask you to look at example 4.9. So read example 4.9. Okay? All right. Any questions? Any questions? All right. Okay, I see some in chat. No, S. Yeah, of course. S, if S start at n naught, then S is bigger than n naught minus 1, correct? What do you think? It's always correct. Okay? I don't need to require it. Okay? All right. What else? Okay. All right, I'm gonna stop AI. I'm gonna stop recording.